Hello and welcome to another math video. This video will start section 2.6 in the pre-calc book dealing with rational functions. And let's go over to bullet points here. This will be covered in two videos. We will find the domains of rational functions. We'll find vertical and horizontal asymptotes of graphs of rational functions. Sketch graphs of rational functions. Sketch graphs of rational functions that have slanted asymptotes. That's definitely day 2 there. And use rational functions to model and solve real-life problems. Now, before we dive into the material, here's a couple of warm-up questions. 2 big rules of math. We don't divide by something, and that would, of course, be 0. Never divide by 0. And also no blank numbers under blank radicals. Well, that'll be no negative numbers. Ooh, my pad is a little glitchy here. No negative numbers under even radicals. Like if you're going to do a square root, you can't have a negative number under there because you can't square root a negative. And that would be the same for a fourth root or a sixth root. We can only have positive values under those even radicals. So here, a couple questions. Find the domain. Well, we said we never want to divide by 0, so we would set this denominator, x squared minus 1, not equal to 0, because we never want it to equal 0. And if we add 1 to both sides, that would be x squared equals 1. And then we would take the square root. X would equal plus or minus 1. So the domain, that should be not equals, not equals. So the domain here is all numbers except plus or minus 1. And I guess we could write it like this: the set of all x such that x does not equal negative 1, positive 1, close set. Or we could write that as intervals from negative infinity to negative 1, and then negative 1 to 1, and 1 to infinity. And notice I use parenthesis there because the parenthesis means we would not include the 1, and parenthesis here we would not include the negative 1. Those are the numbers not in our domain. Now when you see a radical and they ask for the domain, make sure it's an even radical, and then I'm going to take what's under the radical, 2x plus 1, and set it greater than or equal to 0, because what's under a radical must be positive, and zeros are okay too. So if I solve this for x, we're going to subtract 1. Subtract 1, divide by 2. X must be a number greater than negative a half. If you plug in a number less than that, we're going to get a negative under the radical. Like if I put a negative 2 under the radical, that would multiply to a negative 4. Negative 4 plus 1 is negative 3. No negatives under radicals. All right, let's read the introduction. A rational function is in a quotient of polynomial functions. So a rational function looks like a fraction. It's got one polynomial in the numerator and one polynomial in the denominator. We can write it in this form, where nx and d of x are polynomials. D of x is not going to equal 0. The domain of this rational function of x includes all real numbers except the x values that make the denominator 0. Much of the discussion of rational functions will focus on the behavior of their graphs near the x values that we exclude from the domain. So here in example 1, it says find the domain of this function, 1 divided by x. Discuss the behavior near any critical excluded x values. Well, our function is 1 over x. We don't ever want the denominator to equal 0, so we would just set our denominator x not equal to 0. That's a naughty number. We can't plug 0 in directly, but we can use a TI-89 in a table to see what happens as we get close to that value. So here is sort of 0 in the middle. We're going to approach 0 from the left-hand side. So here's some numbers close to 0, like negative 1 is pretty close. If I plug that into the function 1 over x, that'll be 1 over negative 1, or negative 1. Let's get closer to 0. Negative 0.5 is even closer. If I put that under the 1 here, 1 divided by 0.5, or a half, would be 2. So that'll be a negative 2. Negative zero point zero 0.01 or negative zero point 0.1. If I put that under 1, 1 divided by zero point 0.1 is 10, and the negative will make it a negative 10. Negative 10. Next up is negative zero point zero 0.01. Well, we're dividing that into 1. Think $1. 0.01 is a penny. How many pennies are in a dollar? Well, there's 100 of them. And the negative is just going to make the whole value negative. Notice we move the decimal out one more spot, 0.0001, 1,000th. So that will be 1 divided by 0.0001, so that's 1,000, and the negative makes it negative. So let me throw some new notation at you here. As x approaches 0 from the left, this little plus or minus sign up here, it's not an exponent, it's telling you your side of approach. As x is approaching 0 from the left, f of x is approaching, well, let's see, negative 1, negative 2, negative 10, negative 100, negative 1,000. We can get closer and closer to 0 without actually getting there, and that'll just add more zeros to our answer. So where this is heading is negative infinity. Let's hop to the other side of 0. I'll switch to red ink. We're going to approach 0 from the other side, from the right side, from numbers bigger than 0. Well, it's the same function, 1 over x. If I plug this 1 in, 1 divided by 1 is 1. Plug in the 0.5. 1 divided by a half is 2. 1 divided by 0.1, that is a tenth, so when we divide by that, it's 10. Here's a dollar, and we're dividing it by 0.01, or pennies. There's 100 pennies in a dollar, so that's 100. And if we add another 0 in there, 0.001, that becomes 1,000. So down here in red ink, as x approaches 0 from the right, from the plus side, our outputs, our f of x's, look like they're heading for positive infinity. There we go. Find the domain, all the numbers except 0. Discuss the behavior. So as we get close to that, we're heading up to positive or down to negative or infinity. And if we look at the graph, it'll make a little more sense. Here we go. So as we approached 0 from the right, our values started climbing and climbing and climbing. They're heading for infinity. As we come in from the other side here, our values were negative, and they were getting very deep, very negative, very quickly. We're heading down to negative infinity. Now here's where the book brings in that notation. They sort of reverse it from the way I did, but that's fine. In example 1, as we get near 0, here we have f of x is approaching negative infinity as x approaches 0 from the left. And the other side, f of x is approaching positive infinity as x approaches 0 from the right. So this line, x is 0, is a vertical asymptote of the graph, as shown here in the figure. Notice that the graph also has a horizontal asymptote that is the x-axis. So let me move this up here. So, the original function is 1 over x. If we set our denominator equal to 0, we get x is 0. That shows us where the vertical asymptote is, at 0. You can never cross or never touch a vertical asymptote. You can only avoid it by going up to positive infinity or down to negative infinity. So we have our definition of a vertical or a horizontal asymptote. The line x equals a, that's just some number like x equals 3, is a vertical asymptote of the graph of the function when the y values head to infinity or they head to negative infinity as x approaches some number a from either the left or the right. Now here's a different line. Y equals b is a horizontal asymptote of the graph when our function f of x, the outputs, approach that b number as we said x way off to infinity or maybe off to negative infinity. Eventually, as x heads to positive or negative infinity, the distance between the horizontal asymptote and the points of the graph must approach zero. Figure 220 shows the vertical and horizontal asymptotes of the graphs of three rational functions. Here they are. So the first one, our function is right here, 2x plus 1 over x plus 1. It has, we can see here this red dotted line, a horizontal asymptote at a height of 2. And it looks like it has a vertical asymptote hitting negative 1. And let me spoil the surprise. The way we get those, if I take this original function, if I set the denominator equal to 0, I get negative 1. That's the vertical asymptote. Notice the leading terms here are a 2x and an x. They have the same power. They're both x to the first. So we can cancel the x's, and then this is just 2 over 1, or 2. That is our horizontal asymptote going through y equals 2. So let's see what it says down here. Oops. Verify numerically the horizontal asymptote. Create a table of values. We're not going to do that. I'll just get you to the shortcut. Now this one here, 4 over x squared plus 1, it says the horizontal asymptote is y equals 0. If we continued going out, that graph, here in blue, it's going to very much level off. It's going to approach but never touch that x-axis. And if we notice here, the numerator is a lower power than the denominator. Our denominator is x squared. Our numerator doesn't even have an x, so the denominator is more powerful. That means the x-axis is going to be our asymptote. Now this last one here, the function is 2 over x minus 1 quantity squared. If you set that x minus 1 quantity squared equal to 0 and solve for x, you get x is 1. So there's our vertical asymptote. In this case, notice that the denominator, the numerator is positive, a positive 2. Our denominator is also positive because it's some quantity squared. If we have a positive numerator and a positive denominator, positive divided by positive is positive. So both of these, as we approach from the right, is heading to positive infinity. And as we come in from the left, we're also heading for positive infinity. So, and I think this will be on the next slide. Yeah, here we go. Vertical and horizontal asymptotes. Now this is kind of confusing. They got f of x is n of x over d of x. Well, that's our function is the numerator over the denominator. And I'm going to highlight this. This is critical. The numerator and denominator have no common factors. So if we could factor them and cancel, we would want to do so. So you have to cancel any common factors first. And then it says the graph of the function has vertical asymptotes where the denominator is equal to 0. The graph has at most one horizontal asymptote determined by comparing the degree of the numerator and the degree of the denominator. So like if we have x to some power up here and x to some power down here, we're just going to compare those. When n is less than m, let me see here. N and m, I forget what the n and the m's come from. It's got to be numerator and denominator. Oh, there it is. The n and the m come from right here. It's the highest power of the x. You know, x to the n is in your numerator. X to the n is from the numerator. X to the m is from the denominator. So if the numerator is less than the denominator, if the numerator exponent is less than the denominator's highest exponent, then the graph has y equals 0, or the x-axis, as a horizontal asymptote. If they are exactly equal, if they have the same power, then we drop the variables and we just use their leading coefficients. Back up here, I'll use blue ink. When we cross off the variables to the same power, we have these leading coefficients. A sub n over b sub m, those become our fraction. That will be our horizontal asymptote. If the numerator is more powerful, then the graph has no horizontal asymptote. You're either heading for positive or negative infinity. I assume our next example will clarify these. Oh, not exactly. Find all vertical and horizontal asymptotes of each graph. So for letter A, the horizontal asymptotes, I'll use letter H, we're going to set the denominator equal to 0. Or no, excuse me, this is vertical asymptotes. The vertical asymptotes come from the denominator. We're going to set the denominator not equal to 0. And if we work it that way, we're going to add 1. And then we'll take the square root. X cannot equal plus and minus 1. Those will be the vertical asymptotes. When I should have pointed out at the beginning, there's no way to cancel anything, factor and cancel. We can factor the denominator into an x plus 1, x minus 1, but nothing's going to cancel. So there's our vertical asymptote set denominator equal to 0. For the horizontal asymptotes, our numerator is a 2x squared at its highest power. Our denominator is a 1x squared, its highest power. Since it's a tie, we can just cancel the x squareds. And our horizontal asymptote is y equals 2. Now, they didn't ask us to sketch it, so we can stop right there. Numerator equal to 0 would give you the x-intercepts, which they did not ask for. The test, our power is equal. That gives us the horizontal asymptote at 2. And set your denominator not equal to 0 to find the vertical asymptotes. Now, letter B, when I look at B, it looks like we might need to factor it. So my numerator, x squared plus x minus 2, that's going to be an x plus 2 and an x minus 1. Down in the denominator, x squared minus x minus 6. So what's that going to be? Minus 3 and a plus 2. X minus 3, that's a terrible 3. X minus 3 and x plus 2. Okay, now vertical and horizontal asymptotes. If we set these denominators equal to 0, we're going to find two horizontal asymptotes. But remember, we have to factor and cancel first. So if we cancel the x plus 2's, our function now looks like this. X minus 1 over x minus 3. Okay, so if I want to find the vertical asymptotes, VA, we're going to set the denominator not equal to 0. X minus 3 cannot equal 0. Add 3 to both sides. X cannot equal 3. That is the vertical asymptote. That's what's going to zero out our denominator. Now, when we go to do the horizontal asymptote, here's our original function. The highest powers are both x squared. Those are a tie, so they cancel. So our coefficients in front were 1 over 1, or just 1. So our horizontal asymptote is just y equals 1. And I guess we could have got that here in our factored form. You know, here's 1x minus 1 over 1x minus 3. Here the x's are still tied, so we could get our horizontal asymptote there. And I got a graph for each of those, I believe. Yeah, the 2x squared over x squared minus 1. Here's what it looks like. We found two vertical asymptotes at 1 and negative 1, and a horizontal asymptote at 2. What a beautiful graph. A couple for you to try. Find the domain of this. Figure out what's happening as you get close to the value that's excluded, and then find the vertical and horizontal asymptotes here. So pause the video and try those and fire it up and see if you got them right. So for the first one, our denominator, x minus 1, we don't want it to equal 0. So if we add 1 to both sides, we don't want x to equal 1. Is there any way to factor and cancel? No, it's not going to happen. So Now here it says discuss the behavior near any excluded. Well, let's do it like this. We've got a 3x over x minus 1, and we want to figure out as we approach 1. So let's see here. As x approaches 1 from the left side. So think about the number line 1. Give me a number a little bit to the left of 1. I'm thinking 0.9. 0.9. 0.9. Now, if I plug 0.9 in the numerator, 3 times 0.9 is 2.7, but we're just worried it's positive. If I put the same 0.9 in the denominator, 0.9 minus 1 is negative. A positive number divided by a negative number is negative, so that's telling us here our function is heading for negative infinity. And what happens as x approaches 1 from the plus side, from the right side? So I'm thinking of a number a little bit bigger than 1 on the right side of it. I'm thinking 1.1. If I put 1.1 in the numerator, I'm going to get a positive numerator still. If I put 1.1 down for this x, 1.1 minus 1 is positive. So now our scenario is positive divided by positive. That means this limit is heading for positive infinity. So it all comes down to the signs of our numerators and denominators. So find all the vertical and horizontal asymptotes here. Let's find the horizontal asymptote first. We can look at our numerator and denominator. Highest power is squared, so we cancel those. So we're left with 3 over 1, or just 3. Y equals 3. Now to find the vertical asymptotes, we might have to cancel stuff after we factor, so let's factor. Our denominator looks like it'll be the easier of the two. So that'll be an x and an x, two numbers that multiply to 3 and add up to 4. That's got to be 3 and 1. Now, the numerator might be a little trickier. 3x squared plus 7x minus 6. Let's see here. I'm going to use denominator as a clue. I see the 6. I think 6 is going to be 2 times 3. So this will be x and x. Ooh, but I want a 3 in there. 3x minus 2 and x, would that be a plus? Let's see, the outers would be a minus 2x and the inners a plus 9. 9 minus 2 is 7. So that's the combo we're looking for. Okay. So if we set this equal to 0, if you set x plus 3 equal to 0, you'll get x is negative 3. But that's not a vertical asymptote because this x plus 3 can be canceled. So it's not a vertical asymptote. So what we're left with is this simpler function. And if we set this denominator not equal to 0, we're going to get x cannot equal negative 1. There's our vertical asymptote. And I think that's all they were asking for. Find the vertical and horizontals. We did. Set your denominator equal to 0 or not equal to 0 to get your VAs after you factor. And use our little test about the exponent's power to figure out the horizontal asymptotes. Okay, looks like 2 more examples. And these are just going to be sketching a graph. Now, some of these, I don't do all of these for everyone. Some graphs are easier than others, but these are good guidelines. First, your function is going to be a numerator and denominator. The d of x, the denominator, is not going to zero out. Simplify the function if possible. Factor and cancel. List any restrictions on the domain. No negative numbers under even radicals. 0 cannot be in your denominator. Find and plot the y-intercept. That's easy. Just plug in a 0 for all the x's. Find the zeros of the numerator, if there are any. Plot those corresponding x-intercepts. Find the zeros of the denominator, if there are any. Sketch the corresponding vertical asymptote. Find and sketch the horizontal asymptote if it has one, using the rule for finding those asymptotes. Number 6, plot at least one point between and beyond each x-intercept and vertical asymptote. Number 7, use smooth curves to complete your graph. All right, so let's dive in and see what we can, well, technology here. Some graphing utilities have difficulty with rational functions with vertical asymptotes. In connected mode, a graphing utility may connect the portions of the graph that are not supposed to be connected. You'll see this sometimes on our TI-89s. If there is a vertical asymptote, you'll actually see something in there. That's just the calculator freaking out. If we change it over, if there's a dot mode, we might get something a little more accurate, where as we go up, we're just having these more disconnected dots. So be cautious with a vertical asymptote in a computer. Some computers aren't very good at handling vertical asymptotes. Okay, now this one's not going to be too bad. I'm going to just draw an X and Y axis. We can sort of graph this as we go. Step one back here was find your y-intercept. If I plug in a 0 for x, 0 minus 2 is negative 2, so that would be negative 3/2. So I know on my y-axis, negative 1.5 is my y-intercept. If I set my denominator equal to 0, x minus 2 equals 0 or not equal to 0, you add 2, x cannot equal 2. So here's 1, 2. This is positive 2, vertical asymptote. The denominator here is more powerful. There's a 3 upstairs, x to the first downstairs. Denominator is more powerful, so that means the x-axis is a horizontal asymptote. Okay, now it says plot more dots, but let's look at this dot right here. We know we go through that point, so if I'm at this y-intercept and I start heading to the left, I know I'm stuck under my horizontal asymptote, so I'm just going to approach it from underneath. When I cross the y-axis and I'm over here, I'm corralled by the asymptote. I'm not allowed to go back up this way. There's no x-intercept. I can't cross and go anyway. So that vertical asymptote is going to corral me and head me down toward negative infinity. Now, what we don't know is what's going on over here. Like if I choose x is 3 or x is 4, I might be up here in quadrant 1. I might be down here in quadrant 4. So here we're going to need another point. I'm just going to go out here and pick, 4. If I plug 4 back into this original function, that's going to be 3 over 4 minus 2. 3 over 4 minus 2 is 3 over 2. More importantly, it's a positive 3/2. So if I come over here, I'm going to go up to 3/2. That means I'm definitely not down in this part. And I know now my graph is going to be up here. So if I'm at this dot and I start heading to the left, I'm approaching that vertical asymptote. I'm not going to go down because I can't cross the x-axis again. I'm forced to go up to infinity. And as I head out to the right, I'm going to be approaching but not touching that horizontal asymptote. So there's a pretty decent sketch of our graph. Here's what it would really look like. Close enough. Now see here, they did plot another point. They found this one, and they found this one down here. But again, because we're going through the y-intercept, we're sort of corralled by those asymptotes. A couple more points isn't going to hurt anything, but sometimes it's not totally necessary. Ooh. Okay, sketch the graph of this, 2x minus 1 over x, 2x minus 1 over x. And they give us a few clues here. The y-intercept, if we put zeros in for the x's, you'll get 2 times 0 minus 1 over 0. We cannot divide by 0, so there's no x-intercepts. Y-intercepts. X-intercepts, set the numerator equal to 0. So that's 2x minus 1 equal to 0. Add 1 to both sides. 2x equals 1. Divide by a half. X is 1/2. Oops. Get back there. X is a half for our x-intercept. X is 1/2. Vertical asymptote. That's an easy one. Set your denominator equal to 0. So that's just going to be x is 0. That's the y-axis asymptote. The horizontal asymptote. Our powers are both first, so we make a fraction out of our leading coefficients. 2 over 1 is just 2. Y equals 2. Now let's start working on a graph here. Let me make a new slide. So some of the stuff we figured out, no y-intercepts. X-intercept is at 1/2. So if I make this 1, we're going to hit the x-intercept at 1/2. Vertical asymptote is the y-axis, or excuse me, yeah, the y-axis. X is 0. So here's a vertical asymptote. Horizontal asymptote was at y equals 2. I'm going to go up here and call this 2. And here is my horizontal. Oop, no, I shouldn't go quite that high. I'm going to come down here and make this 2. So that's my horizontal. Oop, red ink, there we go. Horizontal asymptote. Now it does say additional points, or we could find these intervals and find some values in between. You know, the big things are the x-intercepts and the asymptotes. So again, if I'm at this point, I'm crossing the x-axis at 1/2, and I start heading to the left, I'm not going to go up this way because I'm stuck under the asymptote at 2. So from this point, I'm forced to go down, and the vertical asymptote is going to corral me toward negative infinity. Now, if I start heading to the right, I'm going to go up, but I'm going to be held under by that horizontal asymptote at 2. So that part of the graph we can do with some pretty good confidence. But what's going on over here at -1 or -2 or -3? Well, let's check -3. If I plug -3, maybe the function's going to be down in this part of the graph, or maybe it's going to be up in this part of the graph. So by plugging in -3, we'll get the location of our function. So 2x minus 1, that's going to be 2 times -3 minus 1, and that's going to be over -3. So our numerator, that's going to be what? -6 minus 1 more is -7 over a -3, and the negatives will divide to a positive. And 7 over 3, that's a number a little bit bigger than 2, like 2 1/3. So if I'm over here, I've got to go up to 2 and up a little bit more. So I'm going to put this dot. Now we know for sure we're up here. So as we head toward the y-axis, that's our asymptote that's going to force us up. And as we head to the left, we're going to approach the horizontal asymptote at y equals 2. So there's our sketch. Turned out pretty good. Here is a better graph from the book. And it looks pretty close to ours. You know, they did find some additional points. They found this point, and they found this point, but, you know, we were corralled by our asymptotes. And up here they found this additional point. You know, we found, well, no, we found 3, 2 1/3, so we found this point. The book found a couple more. But overall, our graphs were pretty good. Ooh, and I guess, yeah, that's our last exercise, or last example. Ooh. Hold on, did I miss this one? Okay, you were probably screaming at your notes. Go back and do example 3. Or did I do this one? Oh no, we did that one. I forgot. When I erased all my work. So there, example 4. The homework is on. Ooh, well, here's a couple huddle problems. Pause the video and try these, and then fire it back up and see if you got them right. All right, the first one. We find the y-intercept. Let's put 0 in for x. So f of 0 would be 1 over 0 plus 3, or 1/3. So if I make this 1, I'll put 1/3 is about there. We can't factor and cancel anything, so set your denominator equal to 0, and you'll get -3. So here's -3, and since we can't factor and cancel, that is a vertical asymptote. When I look at this, our denominator has x to the first. Our numerator does not have an x at all, so the denominator is more powerful. That means we have an x-axis asymptote. All right. Well, you know, we've got this y-intercept right here. So if I start heading to the left from there, I'm going to get forced up by the vertical asymptote. And if we head out to the right, we're going to approach that horizontal asymptote. And if the graph is up in this piece, we're not going to have anything down here, or it would fail the vertical line test. So now let's plug in a number to the left of -3 and see if we're up here or down here. Let's see. I'm going to pick -5. Let's go out to -5. So our function is 1 over. I'm going to plug in -5 and then +3. So that's 2 in the denominator, so that's -1/2. And since I know it's negative, I know I'm under the x-axis. So there's my point. If I start heading to the right, I'm heading toward the vertical asymptote, which forces me down. And if I head to the left, I'm going to be held underneath by the horizontal asymptote. And hopefully your sketch looks a little something like that. Now this one, numerator 3 plus 2x over 1 plus x. And when I look at the numerator, I cannot factor anything. The denominator is as simple as it gets, so we cannot factor anything there. So let's see. If we set the numerator equal to 0, we get the x-intercepts, and that will be subtract 3 and divide by 2. So -3/2, or -1.5. Here's -1, here's -2. We've got an x-intercept right there. Set your denominator not equal to 0, and you get -1. So there is a vertical asymptote at -1. And here's our highest powers in numerator and denominator. It's a tie, so the horizontal asymptote is at y equals 2. Here's 1, 2, and we've got a horizontal asymptote there. Okay, so if we're at this x-intercept, if I start heading to the left, I'm going to be held underneath this horizontal asymptote at 2. And if I head to the right, the vertical asymptote forces me down. So now we got to figure out what's going on either up here or here by plugging in a number beyond -1. Ooh, and a nice easy one to use, it's not always available, but 0. Let's plug 0 in there. And if we plug in 0, these terms turn into zeros. So we're just left with 3 over 1, or 3. So here's 2, here's 3. At 0, here's our y-intercept. So if I'm at this y-intercept, I start heading to the right. I'm held above this horizontal asymptote at 2. If I head to the left, I'm forced up by the vertical asymptote. So there we sketched it, state its domain. The domain are all the numbers not equal to -1, because we don't want to zero out that denominator. Okay, look for the homework on WebAssign, and I'll see you in the next video.